Hey guys, thank you for joining. My name's Omar Zoni, and in this video series that we're doing with my colleague Sashi, we're going to be covering SIMULIAworks, which is a really exciting new collaboration between the SolidWorks brand and the Simulia brand. Now, the Simulia brand inside of Dassault Systems is responsible for all of our simulation capabilities, and they develop a product called Abacus, which you have probably heard of. They also they're responsible for all of the simulation capabilities inside of Dassault. So our flow solvers, magnetic solvers, acoustics, fatigue and fracture, systems analysis, uh, basically everything. And in this particular webinar, what we're going to be talking about is the advanced meshing capabilities as well as the generalized contact that's available inside of SIMULIAworks. So let's go ahead and get started. We're gonna look at a couple different models. The first one being a honeycomb structure. Here's the first model that I want to take a look at. So this is meant to mimic a honeycomb structure. The material property is going to be a relatively compliant hyperelastic silicon. Uh, the boundary conditions for this are relatively straightforward. So the outer section is going to be fixed, and then there's a structure in the center that we're not modeling. We're going to use a coupling inside of the 3D Experience platform that will pull the center portion down and could also potentially apply a rotation to it. So when we do that, when that displacement is applied, these circular cutouts throughout our structure are going to potentially collapse on one another. So if we were going to set this up inside of SolidWorks simulation, we would need to specify contact pairs. So you'd have to know you'd have to kind of use a little bit of insight into figuring out which faces could potentially be collapsing on themselves, or which faces could be coming into contact with another face in another circle. So that's could be a lot of contact pairs depending on how much displacement we're applying, depending on how compliant our material is. And if we're trying to correctly size this to be able to withstand a certain amount of rotation or a certain amount of displacement, maybe we need to play with the number of holes, the size of the holes. It could get relatively complicated. So the SIMULIAworks tools basically use a completely different approach to handling contact. And we'll talk about that in both examples, that there are some really unique things that the SIMULIAworks tools can offer us. Now, another thing that SIMULIAworks offers us is the ability to create a brick mesh. So we can see this is a fixed thickness, relatively simple geometry to brick mesh. We would just, apply kind of a surface mesh and then sweep that surface mesh through the thickness. Using a brick mesh numerically can help the solver reach a converged solution. When we use tetrahedral meshes, that there's a little bit of non-symmetry. Well, there can be a lot of non-symmetry that gets involved, as well as the fact that sometimes you have tetrahedral elements that will collapse on each other. They can also be a little bit more stiff than brick elements. Because we're using a hyperelastic material, we're also going to use the H elements that are available inside of SIMULIAworks, which are more well suited for hyperelastic materials. So there are a couple ways that we can get the model into SIMULIAworks. So there's a nice PLM services connector is what we're calling it. And basically, we can take this model. You can see it's called Rev A1. Basically, it gives us a little bit of PLM control on the 3D Experience platform. So it's connected to this model. We can upload the model, run it, and then if we needed to make any changes on the SolidWorks side, we could make changes in SolidWorks, update the revision number, and then kind of automatically update our analysis on the platform to mimic, so that we don't lose the A1 results. We could have like a B1 or a C1 revision, and then just apply or run the analysis on those new revisions. So I'm not going to use that strategy right now. Maybe we'll use it in a future model. I'm just going to use the direct import capabilities, but just be aware there are some different paths to import the model into the platform that could allow you more control if that's something that you're interested in. So this is the model pulled from SolidWorks here on the 3D Experience platform. Now, I'm not going to spend a lot of time kind of going over a lot of the steps in detail, but I do want to point out a couple things. So in the 3D Experience platform using any of the SIMULIAworks tools, whether it's structural professional engineer or structural performance engineer or structural mechanical engineer. Um, you're going to spend your time in 3 or 4 different apps. So there is the model app, which is here. There's the meshing app. You might spend a little bit of time in the model prep app. You'll spend some time in the scenario app and then in the results app after you've run. So there's a very nice feature manager here that allows you to hop between your modeling app and the modeling app features, your scenario app and the scenario app features, and then your results. Your plots, XY plots, contour plots that you've predefined or added. So the model app, the feel is a little bit different than SolidWorks desktop simulation tools. The modeling app is basically where you're going to define kind of geometric modeling features. So for instance, I'm saying that this body right here is going to be modeled as a solid section, not a shell, not a beam, and I'm applying my material property, which is a hyperelastic material. This is also where you define the type of mesh that is going to be put on the body. So I'm going to use a swept 3D mesh, and I'll walk you through some of that stuff. So let's talk a little bit about first the material property that's used. So I'm going to do that by just kind of hopping into the materials palette. So the material palette are where all of your predefined materials are. If you want to create a new material property, this is where you would do it also. So I'm just going to look at the materials that are in session, which means are included in this model. And I've only got this one. Now, if I look at my simulation domain, you can see we've got a density defined. It's very close to water, right? This is a hyperelastic material. And then with respect to the material model, you can see we're using the Yao hyperelastic material model. And this, we'll talk about this in another section and exactly why we're using this model. It has to do with some curve fitting. So we got this data and we actually fit it to a curve. But let me point another couple things out here. You can see there are a whole host of different material models that are available to capture your hyperelastic material. You can see there's a really nice material for foam. There's some porous elasticity. You'll notice that the material definitions that are available inside of the SIMULIAworks tool are a little bit more robust than what was available inside of SolidWorks and the desktop simulation tools. All right, so that being said, now let me take you over to the meshing app. Now the meshing app is where you'll specify, your two-dimensional meshes. If you're using shells, it's where you'll define your TEP mesh settings, your solid mesh settings. In this case, let me just pull up the part mesh manager because we've already defined our mesh on this guy. So if you had multiple parts, the part mesh manager would be where you could walk through and look at the settings for each individual part. So you can see for this guy, I'm using kind of a seed size of 0.5 millimeters. So that's basically saying, these elements on the face are about 0.5 millimeters, and I'm saying I want 3 elements through the thickness. And you can see we've got our 3 elements through the thickness. So obviously I've got full control over that. There's some really fancy things that you can do if you want to have more control over your seed mesh, kind of your face mesh before you extrude it through the thickness. Now the other thing that is shown here is, and let me go ahead and turn the model back on. You see this in the center. So what I've done is basically I've created a coupling that basically is where I'm going to apply my loads, my displacement load. So these 4 faces are connected to a kinematic, kind of a rigid center coupling, and that's going to control my displacement or rotations that I apply on that center body. And with respect to how things are held, let me just turn off the model again, the finite element model. You can see I'm applying a rotation of 45 degrees, and that rotation is applied about the z-axis, I believe. So it's basically rotating it, about this axis right here, this short axis. I'm also, the translation is 35 millimeters. And that's in this direction right here, this longer axis. And then I'm just saying that I'm going to clamp the outside. So these outer faces are basically fixed, so they can't move. Now, again, one of the real benefits here of using SIMULIAworks is the way that it handles contact. So I have not specified any contact pairs. What I have done is I've said, look, for this type of silicon, the friction coefficient is typically a little bit higher. It can actually go all the way up to 1. I'm saying that I've got a tangential frictional coefficient of 0.75. And then what I'm doing is I'm basically specifying a global contact. So I'm saying all the surfaces, whether they're in contact now, whether they're not in contact, as they move through the analysis, every surface could potentially come in contact with any other surface. I don't have to manually specify individual contact pairs. The generalized contact here inside of Simulia, really, really powerful. So I'm saying, look, no penetration contact. Assume that I'm using my friction coefficient kind of contact property, which specified the friction coefficient to be 0.75. With respect to the output, it's similar to SolidWorks in that, this is a nonlinear analysis. I'm making the assumption that my load is applied from a time 0 up to 1. And then it's going to take steps. It's going to incrementally step from 0 to 1 for all of my loads that are applied. I'm telling it that I want 100 results stored. So basically, a result stored every 0.01 pseudo time step, right? So let's take a look at exactly what the results look like. Okay, guys, so when the simulation finishes, just like with the desktop product, there are some pre-populated things that you can visualize. So for instance, I can take a look at von Mises stress. And I can walk through any of the results. Now, I should tell you guys, this thing ran to about 50%, and I killed it. It was starting to struggle around that time. The displacement and the rotation that I applied, I kind of arbitrarily picked, but I do think, this shows some really, really interesting and powerful capabilities that are available on the platform. So let me animate this, and it'll become obvious, right? So first of all, how could you have predicted some of these faces that came into contact, right? Imagine if you had to set out and create the appropriate contact pairs for this stuff, right? So we've got the rotation as well as the displacement. Let me turn on contact pressure, and we can take a look at the contact pressure is kind of later in the run. I'd also point out that this, I'm not sure that you would get this far using the desktop product. I think, this is an instance where, having the power of the Abacus solver really benefits us and is a type of problem that we wouldn't have been able to solve inside of the desktop tool. So here we can see an animation of the contact pressures, and you can see as it gets further down in the run, we do start to accumulate a little bit of contact pressure. So let me just pause the animation, and let's go to one of the last steps, right? Kind of zoom in here. So you can see the areas where you're getting contact, right? Basically, a lot of these inner circular cutouts are seeing some contact. Also, though, we're getting some contact pressure out at the edges. Again, this would be a really difficult problem to solve with the desktop, and having to define these arbitrary contact pairs would also be something that's difficult. And if we wanted to see, for instance, what the force or torques that were required to achieve this level of displacement and rotation, we can take a look here. So this is showing us the forces and the moments, basically the force and torque. So the force and the moment required to achieve those values. This is showing them both at the same time, but you can see they're both kind of following the same trajectory here, and there must have been a whole bunch of things that came in contact here that's changing kind of the stiffness of the model, and that's why our response looks a little bit different. So again, a really, really powerful and easy way to capture contact and kind of arbitrary contact, because that's where things really get tricky, right? Where you don't know, um, or you've got a lot of potential contact pairs and you just don't want to have to predefine them. So this is the first example I wanted to show you. Right, so the next model here is another one that I really want to highlight the benefits of the general contact algorithm that's being utilized in the SIMULIAworks tool. So it's a relatively simple two-gear assembly. What we're going to do is we're going to use a coupling to drive one of the gears. So we're going to rotate one of the gears 360 degrees. But what I want to point out real quickly is what you'll notice is there's a bit of interference between the gear teeth here to start. So the way that we're going to handle this is we're going to first do an interference fit as the first step. To kind of resolve that initial interference. Then we're going to go ahead and rotate 360 degrees. And we can look at things like plastic strain in the teeth. We can also look at the amount of torque required to drive the motor. So in order to do this, what you guys are going to see is, I've got my two couplings specified. And yeah, I'm using a tetrahedral mesh for both gears. I'll show you what that looks like. I'm using a carbon steel. I'm including plasticity. But in order to resolve the interference fit, so this is going to be two steps. You can see I do the interference and then the 360-degree rotation. I am actually using what's called contact initialization. And with contact initialization, I just say, hey, go look in the model, find all of the faces that have interference, initial overclosers, and treat those as interference fits. And then in my general, that's all I need to do. So I don't have to grab the faces. I don't have to search for them. I create a contact initialization. I've got a contact property here specified that just sets my friction coefficient to be 0.1. And in my general contact, all I do is I say, look, I want you to use a contact initialization assignment, which is that first contact property. And for any of the faces that aren't interfering, it knows that, it's a no penetration contact, because that's kind of the default. So let's take a look at the results. Well, first let me show you the mesh. I didn't use a really fine mesh for this. I didn't feel like it was necessary. Again, obviously, if you wanted to get more accurate results, you're going to have a much finer mesh, right? But a relatively coarse mesh, I think I'm using parabolic tets in this case. And if I look at the results, let's first take a look at the interference step. So you can see in my interference step, if it's going to try to resolve the interference. I'm just going to go to the end of the step, because what you'll notice is there's some plastic strain, right? We're looking at plastic strain here, and you can see there's some plastic strain in those interfering teeth. So first we resolve that interference, resolve that plastic strain, and then we go ahead and we rotate 360 degrees. Again, remember, I'm not setting any manual contact pairs. So then I go to my rotate step, and let's go ahead and just play it. And it will actually play both steps for us. So you can see it's highlighting a plastic strain. We're getting a lot of plastic strain in those gear teeth for the 360-degree rotation. So really, really cool analysis here. Again, so simple to set up, taking advantage of including plasticity in the material model. It's including interference fits. Another really cool thing we can do, because we've utilized those couplings, is we can create XY plots that kind of highlight the amount of torque required to drive the gear. So you can see, the first, or from this initial part is probably the first step where we're not really rotating. And then from 0 to 360, we can see the amount of torque it's requiring. So to get back to that initial position that it was in, you can see it requires a little bit more torque, about 55 or 6, about a little over 55 newtons per meter. So if we wanted to mess around with the teeth, we could do that, mess around with the material properties in order to minimize the torque. But again, really, really simple, complicated analysis that we can do pretty much push button here, not having to set up those manual contact pairs. So I hope those two examples were useful for you guys to see. And this is just scratching the surface of what SIMULIAworks can do. Again, I would advise you guys to continue to check in. We're going to be doing, I think, a 4 or 5 part series here related to SIMULIAworks. Trying to connect with you guys during these difficult times. A couple places that you can look for resources. If you go to solidworks.com, there's a section on SIMULIAworks. You can learn about structural. It's been changed from structural professional engineer to now structural performance engineer. Some really good content there. Also, if you have access to my SolidWorks, you can look for Simulia Structural, and there's actually a video with my smiling face. You guys can take a look at that shows some of the capabilities available inside of SolidWorks or SimuliaWorks. And here are some other capabilities. So this is Sashi and I are going to be presenting on another product called Structural Mechanics Engineer that accesses the Abacus explicit solver. So some of the stuff you're seeing here, maybe all the stuff, is Structural Mechanics Engineer. So the explicit solver is so cool. The stuff that we're going to be able to do. All on the platform. And we didn't even talk about one of the real benefits of the platform is the ability to collaborate and share results. So all this data is stored up in the cloud. Someone can log into the platform really, really easy. There's really great ways to share this data. And in a situation like this where we're all working from home, I mean, the 3D Experience platform is a really powerful tool that allows us to leverage and be collaborative while we're sitting at home working in the home office. So if you guys have any questions, please email me, omar.zoni@3ds.com. I'll leave this up here for a few seconds before we wrap up. And again, everybody stay safe. It's a really weird time right now. We're doing our best to stay engaged with you guys and be here and be helpful in any way that we can. If you guys have any questions related to 3D Experience platform, even SolidWorks CAD, anything I can help with, please feel free to send me an email. My expertise is on the simulation side, but I will direct you guys to the right people in the likely event that I don't know the answer to your questions. So anything we can do to help, please let us know. And again, stay tuned. We got a few more videos that are coming out that are going to be really, really neat. So thank you guys. Cheers.